So our next chapter is chemical equilibrium. We take them in order of chemical kinetics first, because equilibrium is dependent upon kinetics for its definition. All right. So what do we mean by chemical equilibrium? It's based upon concentrations of reactants and products. So if you've got any number of reactants yielding products, you will have an expression of concentration for the reactants and the products at the point where they apparently don't change. In other words, the concentration seems to be constant for the reactants and constant for the products. Now, they may start out with nothing but reactants like we did with the method of initial rates. But eventually, you'll reach a point where the concentration of reactants, concentration of products will not change. That's what it looks like in the macroscopic world. But in fact, there is furious activity in both directions. Reactants are making products, and products are remaking reactants at the same time. And the reason we don't think that there's any change in concentration here or here is because they're happening at the same rates. So in other words, the macroscopic looks like it's static, but the microscopic is very dynamic. There's lots of movement going on there. For this example of a reaction, this is my favorite, the Haber-Bosch process, where you have nitrogen reacting with hydrogen to make ammonia. If you start out with nitrogen and hydrogen in their concentrations, you'll see that they have a certain amount on the scale, but there's no ammonia to begin with. And as time proceeds, their concentrations appear to remain constant. At that point, we say they're in equilibrium. So it's all boiled down to the rates. The rate, you'll have a forward reaction here based upon kinetics. We'll have a rate constant for the forward reaction. Then we'll have another rate constant for the reverse reaction. But the rate itself, in other words, if we write, remember how we wrote the rate law? Rate equals K times reactant to some value, some order. And then for the reverse reaction, we could say the rate of that reaction is product to some value. And regardless of what these values are, these two values right here are equal. The forward rate and the reverse rate are equal. That's when you're in a state of equilibrium. We can look at it this way on that graph. The forward rate of one reaction is in the red line, and that rate is dropping. And the rate of the reverse reaction is increasing until they meet. And then both rates are the same. Now, this slide is sort of a teaser for your next lab. If we have water plus carbon monoxide yields hydrogen and carbon dioxide, what would happen? Let me write it up here. Water plus carbon monoxide yields hydrogen plus carbon dioxide. Once we're at equilibrium and the rates are equal forward and back, then what would happen if we add more water? Well, based upon our kinetics, right, if you increase the concentration of one of the reactants, the rate's going to increase, correct? Yeah. So the rate's going to increase, though, until we produce enough of these that the reverse reaction rate equals it. And they meet again. And you reestablish equilibrium. So in terms of shifting equilibrium, when we add a reactant, we're going to shift the equilibrium to the right until we get another balance point. If you add more hydrogen to the other side, and it's in a state of equilibrium, then it's going to go reverse until you find that balance point again. All right, so the equation, we have an expression for the equilibrium in terms of concentrations. It's called the law of mass action. So I like to take coefficient of small a for this reactant A, and then the coefficient of B, and then we get little c and little d as our sample equation. And if we write the law of mass action, it's going to be, let's see, what else do I have in here? Yeah, that's important. The expression that I'm about to give you was proposed by two Norwegian chemists, Peter Wake and his brother-in-law, Cato Maximilian Goldberg. And the expression would be this equilibrium constant is equal to the concentration at equilibrium, the concentration of C to its coefficient power times D to its coefficient power. So the products are in the numerator and the reactants are in the denominator. Like that. Now that's a different K value. Maybe I should write it differently than the rate law K. Let's see. Yeah, they were working with solutions, so they naturally expressed things in concentration units of molarity. When you see a square bracket in an equilibrium expression, it means molarity. Moles per liter. Even if it's a gas, it'll be expressed in molarity. There you go. Yeah, let me use a big K. The little k implies that we're talking about a rate rate law. A big K refers to equilibrium. So if you recall any of the equations that we've studied so far, these coefficients could be almost anything. All right, so if we tried to keep track of the units, right, we have units in here, and if the units are squared or cubed or fourth power or whatever, and you have this conglomeration, you could end up with who knows what as units. So to simplify things and avoid confusion, we don't give the units for an equilibrium constant. What we do say is what are the concentration units that were used to calculate the K, right? Were they molarity? You could also use partial pressures if the reactants and products are all gases. You can use partial pressures. And then we would write the expression K in terms of partial pressure would be pressure of C to the C power, and the pressure of D to the D power, and the pressure of A to the A power, and the pressure of B to B power. Now these values are going to be different. They will definitely be different because they're different units of measure. But they are related, and I think we get to that in a couple of slides. All right. Now, we're going to need to manipulate these expressions and combine them at some point. So we need to know some rules. If we have an equilibrium constant written this way, this is for the forward reaction. Right? If we flip this equation around and put these on the product reactant side and the reactants on the product side, then this value becomes the inverse. So the equilibrium expression for the inverse reaction is just, will be A on top. If you were to actually calculate. But if you have the value for this one and you want to know what it is in reverse, then you just take the reciprocal of this value, right? So this would just be 1 over K. If we multiply, if we have to multiply the equation by a constant factor, then what does that do to the K value? Right? If we multiply this one times, say, let's say N. I suppose we were going to add equations together. Remember Hess's law. If we were going to multiply N times one of these equations, what would that do to this expression right here? Well, it would be N times each one of these, wouldn't it? N, 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 and N. So what would that do to this expression? Well, each one of these would have an N in front of it, wouldn't it? Okay. So what you can do is factor that N out. So now K becomes, I'm sorry? See, A, and B, the B, and factor the N out. Yeah. So the new K value, if we multiply this whole equation by a number, a factor, this then becomes the new K, let's say new K, equals the old K to the N power. Okay. All right. All right. Remember, this is a constant. And the only thing that'll change that constant is temperature. As long as the temperature is the same for a K, the K will be constant no matter what we do with these values in here. All right. All right, there's a difference between the equilibrium constant, which is this. This is the constant. Versus the equilibrium position. If you start off with a certain amount of A and B, then you'll get a forward reaction until the reverse reaction equals its rates. And you'll get new values. The A and B will be lower than they started. C and D will be something. And you'll get you can calculate a K value. But the concentrations of A, B, C, and D give you an equilibrium position. Now, if you either start with a different amount of A and B, or you start with a mixture of A, B, C, and D, or if they're at equilibrium, you add something, or you take something away. You cause the equilibrium to shift, and that will give you a different equilibrium position. So you can have many equilibrium positions, but it's always for a given temperature, the K is always constant. Now, as far as the K value goes, some Ks have subscripts that have special meaning. If we just write KQ, doesn't matter. It's usually molarity is the value for KQ. If you say KW, that has a special meaning for water, because water can, we'll get to this in the next two chapters. Water, pure water, is in equilibrium with hydrogen ions and hydroxyl ions. Okay? So you can get a concentration here and a concentration here, and that'll give you a K value at a given temperature for water. So W is reserved for water. Ka is an acid dissociation constant. So if you have an acid like, let's say, let's pick a weak acid. Right? Acetic acid, right, in aqueous solution, and it's going to dissociate into a proton plus the acetate polyatomic ion. Okay? That sets up an equilibrium also, and that will have a characteristic K value at a given temperature. In fact, one of our labs, we're going to determine what that K is for acetic acid experimentally. Okay, another one possibility, solubility product. We'll get to that one in a subsequent chapter. So I'm not going to talk about it right now. And then we're also going to do an experiment with this one. Let's say formation constant, where we get the combination of a metal and a ligand group, we call it. And we can determine what the equilibrium is between that combination of metal and ligand versus the independent metal and the independent ligand. And then the Kp goes for, well, I erased it. Kp is an expression for equilibrium when we are using partial pressures for a reaction in which all the reactants products are gases. All right. There are probably some more, but those are the main ones. All right. So for this Haber-Bosch process, we would write either a K in terms of molarity on the right. We have ammonia to the second power because that's the coefficient. And then the denominator, we have nitrogen to the first power and hydrogen to the third power. And that would give us a K value as long as we know what those concentrations are at equilibrium. We could also write it in terms of partial pressure because all reactants and products are gases. So the partial pressure of ammonia to the second power, so forth. But they are related. And I think the next slide should show us. Not yet. Okay, if equilibrium pressures at a certain temperature are these values, right here, then calculate the K in terms of partial pressure. So we just plug in those values. As long as they're in the same units, like they could be atmospheres, they could be pascals, they could be pounds per square inch. As long as they're all in the same units, then you can plug them in. And that would give us the KP. All right. I should have written this up here before. Plus hydrogen. Gas. In equilibrium with ammonia. When we calculate that value, and we P equals 3.9 times 10 to the fourth, what does that mean? If we break it out and say partial pressure of ammonia to the second power divided by partial pressure of nitrogen to the first power times partial pressure of hydrogen to the third power, what does that mean? That means with this very large number that it's mostly the equilibrium under these conditions is mostly to the right. Because the numerator has to be huge to give you that value, and the denominator has to be relatively smaller. So you can tell from the equilibrium constant whether the reaction is favored to the right or to the left. If it's a very small number, if this were -4, it would be that direction. And like I said, that value will change with temperature. Like when Haber was first trying to make this thing work, he was running his experiment at 800 degrees Celsius. And that temperature meant that the reaction was going to be this way mostly instead of that way. So this value must have been developed from a very low temperature. Okay, so I said earlier that the KP and the KEQ were related. And this is how they're related. I don't have to memorize, so I'm going to cheat. RT to the change in N. Okay, so this R is going to be, see what value is it? I think that's the 0.08206 liter atmospheres per mole K. Yeah, because this is going to be in atmospheres. Okay, but what's the delta N? The delta N is the change in moles of gas. So we would take the total moles on this side is 2. And the total moles on this side is 3 plus 1 is 4. So N equals -2. So we put a -2 in here. Whatever temperature we're given, 0.08206 here. And if we want to solve for this one, we leave that one as our unknown. We put this value in over here and solve for that one. So they're related by the gas constant, by the temperature, and by the change in moles. Products, total moles minus reactants, total moles. And the temperature, of course, has to be in Kelvin. Oh, all right. So we got this example. All right. 308. 35 degrees Celsius is 308 K. And we put those values in. This is -2. Got a temperature, got a constant, got this constant. Solve for that one. And the K in terms of molarity is not 3.9, but 2.5 times 10 to the 7th. All right. So we're gonna throw the homo hetero at you again. So what's a homogeneous equilibrium? That's where all the reactants and all the products are in the same phase. This would be a good example. They're all gases. That's homogeneous equilibrium. Or if all the reactants and products are in aqueous solution, that would also be a homogeneous equilibrium. A heterogeneous equilibrium is where you have different phases involved. More than one phase. In fact, our examples have liquid gas for water and solid gas for potassium chlorate decomposition. Now, when we write the equilibrium expressions for a heterogeneous equilibrium, let's take the top one. 2KClO3 is a solid. Right? And then we're going to decompose it. All it takes is a little heat or light. You could shine ultraviolet light on it and cause it to decompose. This is a gas. How would we write that expression? Well, the rules are the concentration must be able to change in order for an equilibrium constant to have meaning. So which ones of these can change concentration? Solids don't change concentration. They can react, sure, but they react until they're all gone. Right? Or their concentrations do not change. So we don't include solids in our equilibrium expression. So instead we would say KEQ for this reaction is simply oxygen to the third power. That's it. Okay. For water, the decomposition of liquid water to hydrogen first. Okay. Hydrogen first. And then oxygen gas. Same thing goes for pure liquids. Water would be one of those. Pure liquids are not included in the equilibrium expression. So this equilibrium expression would simply be hydrogen squared times oxygen to the first power. That's it. So homogeneous equilibrium, as long as they're either gases or in some sort of solution where the concentrations can change, anything else is not included in the expression. Okay. I didn't realize I had this slide set up. Pure solids and liquids are present. They're not included in the expression. Now, I have issues with this slide. I'm not sure why I keep it in here. The extent of a reaction, predicting whether a reaction is primarily to the right or to the left. That's probably why I changed the wording. Originally, the slide said if K value is larger than 1, that means that the equilibrium system will consist of mostly products. And the equilibrium lies to the right. But with all these coefficients, possibilities, that doesn't hold water. What can happen is, and that's why I said much larger. If K is much larger than 1, then yeah, you're pretty safe saying that the reaction is mostly to the right. And if it's much, much less than 1, it's mostly to the left. And if it's very large, positive value, then the reaction essentially goes to completion. All right. If the equilibrium lies to the right, the value of K is large or greater than 1. If it's to the left, the K is small or less than 1. All right, now that we've learned how to write equilibrium expressions, there's another way of writing an expression that's not equilibrium. So if you have a system that you mix some reactants together with some products and you want to get some idea as to which way it's going to move, because it's not at equilibrium yet. If it's at equilibrium and you change the concentration, you can predict which way it's going to move. But if it's not at equilibrium, you need an idea of whether the reaction is going to move to the left or to the right with the way you set it up. And that calculation is called Q. Rather than a K, we calculate a Q. And like I said before, it's not at equilibrium, but you are given concentrations and you calculate a Q. Now, why would we want to do that? Well, we compare the Q to the K for that reaction. If the Q and the K are equal, let's write one up here. Let's go back to our generic. Okay, so our K would be C to the little c, D to the little d, over A to the little a, and B to the little b. If we calculate a Q for that reaction, and the Q is equal to the K, that's the easy one. It means the reaction's at equilibrium right now. Okay, what if the Q is greater than K? If Q is greater than K, what does that mean? That means that you have too much product. Right? Q is larger than K. That means the numerator is bigger than it should be. And if that's the case, then the reaction is going to move to the left. As written. Whenever we say left and right for an equilibrium to shift, it must be referenced to an equation, to a balanced equation. If you say left and right and you don't say what equation it doesn't mean anything. It could be it moves left and right because it's a little funny. Okay, but if Q is greater than Q is less than K, if Q is less than K, that means we don't have enough product. And then the shift is to the right, as written. Now, why would we need to know that? Well, we're going to need to know that for doing equilibrium calculations. Because if you don't know which way it's moving, you can't calculate the outcome. All right. So consider this reaction. That's what we're going to do right now. Equilibrium calculation. In fact, I think equilibrium calculations are infinitely easier than kinetic calculation. So we have iron 3+. These are all in aqueous. Yeah, they're in aqueous. We're going to react it with thiocyanate ion. Yep. And it yields Fe3+. No, I don't have to write that there. FeSCN. And a minus and a 3+ is a 2+. Okay, that's our equilibrium situation. If we start off, we set it up with 6 molar in this one, 6 molar, and 10 molar in the thiocyanate. And in equilibrium, the concentration of this one is 4 molar. Now, why did I write it down there? Well, I'll show you. What I'm setting up is called an ice table. This is the initial concentrations, and this is going to be 0, right? Because that's where we set it up. C is for change, what change is experienced, and then E is for equilibrium. And so we're going to have this, this, this. All right. So if we have 4 molar over here, where did it come from? It came from here, right? And these are 1 to 1 to 1. That means if this ended up at 4 molar, that means we had to get 4 molar from somewhere. And we got it from here. Right, 1 to 1 to 1 means we lost 4 molar here, and we lost 4 molar here. So what will be the equilibrium concentrations then? 4 from 6 is 2. And 4 from 10 is 6. Now we have the equilibrium concentration. And we can calculate a constant. All right, so the constant here, I'm going to write it over here because that's going to change in a minute. So we would have 4 molar to the first power divided by 2 molar. Then we don't need to put those in there because we're not going to keep them anyway. And 6 molar. Right. So 4, let's see, that's 2 divided by 6 is 1/3, right? 0.333 should be K. There we go. And there's the ice table we set up. 2, 6, and 4. We calculated the value for K under these conditions is 0.333. Now, as long as we don't change the temperature, that's going to be the K no matter what we do up here. We could change these values. And once we find out what these are, it's going to be equal to that. And I think that's what we're going to do next. All right, suppose we change the initial concentration to 10 molar. Change this one to 10. And thiocyanate to 8. Yeah, it's got an 8. This one does. Same temperature. What's the equilibrium concentration of this one? This value down here. So we want to know what this is right here. Let's see, did I work it out? Yeah, I set up a table. We still got 10, 8, and 0. And if we know we're going to end up with, which way is this reaction going to move? That's the first question. Well, we've got no product, so it has to move to the right. And it's going to produce some amount. Where did it come from? Well, 1 to 1 to 1, it came from here and here. Same amount for both of them. So that means we're going to have X here. We're going to have 8 minus X here. We're going to have 10 minus X there. So if we set up our equilibrium expression with these unknowns embedded, and by the way, when you're setting up an ice table, if at all possible, if you've got to include an unknown somewhere, try to pick an unknown that when you solve it for that unknown, that'll be your answer. So in this case, this is our answer. Otherwise, you got to go back in and do another calculation to find your answer. All right, so this 0.333 is going to be equal to x divided by 10 minus x times 8 minus x. And we just solve for x. Now, here's the next problem. If you have to keep all your x's, then you're liable to end up with a quadratic equation. Then you have to solve the quadratic. That's why, I think I still got it, yeah. I still got my quadratic on the back of my calculator, so I don't have to remember it. Remember, minus b plus or minus square root of b squared minus 4ac all over 2a. Yeah. So, and what we're looking for is an ability, if at all possible, to eliminate these x's. The problem is this value tells us that those x's are substantial changes, right? Those values are large enough that we can't eliminate them. Now, there are two ways to approach it. If you're going to have a quadratic equation, then fine, just use the quadratic. If you've got one that has some odd powers in here, then sometimes the best approach is called the successive approximations, in which case you will drop those x's, find out what that x is. Then you go back in there and do it again, only this time you take that x that you discovered, and instead of putting it in here, you put it there and there. Calculate it again. And that may take a couple of tries to get there. If you've got a computer program set up to do it, then this is no problem. And that's the way more complex reactions are determined. Just let the computer do the approximations. So rather than do all that on the board, I'm just going to reference the expression here. And if we solve for x, remember, in order for the quadratic to work, you need x squared x and the, we call that a coefficient, do we? All of it equal to 0. Then you've got your a, b, c values, and you can plug them into your quadratic. And since there's a plus or minus there, you've got two choices. You're going to have two answers. You got to decide which answer makes sense. Well, if x is 15.99, right, subtracting 15.99 from these is going to give me a negative number, so that can't be it. 5 is the only possibility. If you subtract 5 from each one of these, then that'll work. Now, there's a way to tell if you're going to do the successive approximations, or if you have the opportunity to drop the x's. And we'll talk about that in a minute too. But if you do make those assumptions, then there's what's called the 5% test. You take the value that you determine as your x and put it back into the real expression and calculate what k would be with that x in there. Then you compare that k to the real k and see if it's within 5%. And if it is, then your approximation was correct. Okay, we got another one. Right, I'm not going to go through that one. We just changed the values. So now we're going to have a different equilibrium position. But the k is still a constant. And that comes out to be, with those different concentrations, 6 and 6. The equilibrium concentration now, instead of 5, is 3. So that is a different position. All right. You always have to have a balanced equation. That's the same for this approach, for stoichiometry, for anything. The balanced equation tells you what's happening at the molecular level. Then you write the equilibrium expression using the law of mass action. That's fairly simple. Once you have the balanced equation, it's easy. Then you list your initial concentrations, right? Set up your ice table. If you have to, calculate the Q. Right? If you're given a value here, here, and here, then you may have to calculate the Q to determine which way it's going to move. Because if it moves this way, then this is going to be a minus and these are going to be pluses. But if you have one, like if we have something here, here, and nothing there, then you know it's going to move this way to put something in that space. I like those because you don't have to calculate the Q. All right. This emphasizes the fact that if at all possible, choose your X so that it is the answer. If at all possible, do that. And that'll save you a step or two. Then you substitute your concentrations into the expression and solve for the unknown. And then check your calculated equilibrium concentration with the correct value for K and see if it's within 5%. Oops. There. Okay, we have these other possibilities, right? We could put these values in. Now, if we start off with 9, 5, and 1, then we would need to calculate a Q. Why don't we do, let's just do one of them. That erase my E. There, there, there. So our first example is 9 molar here. And then 5 and 1. 5. 1 molar. Okay. So let's calculate a Q for those values. Right. Q then would be 1 over 9 times 5. I think we can figure that one. 1 divided by 45 is going to be less than this. So if Q is less than K, that means this is too small. It's going to move that way. So now we know we could say we wanted us to calculate concentrations of all species. And so make this one X. Yeah. So we're gonna add some on this side, like 1 plus X, and we're gonna subtract, since it's all 1 to 1 to 1, we're gonna subtract an X from here and subtract an X from there. That makes it 9 minus X here and 5 minus X here. Then, plug them into the equation, find out what X is, and then you take X and add 1 to it. That gives you this concentration. Take 5 minus that X, 9 minus that X gives you those concentrations. And that's your equilibrium position for that starting point.
So if it was greater than 0.33, it would be, the first column would be X plus, go the other way.
Calculating Q?
Yeah.
Okay. If we calculated the Q, say, the last one, 6 over 18 would be the Q for that one. 6 over 18. So that would be, that's equilibrium. 3 times 6 is 18. So that, yeah, the last one's at equilibrium. Well, maybe we'll pick the other one. 5 divided by 6. 5 divided by 6. So that's larger than this one. That means we've got too much of that. So it's going to move this way. That'd be a minus and these would be pluses. Right. Okay. We can move on. Oh, there are answers. Answers. That's okay. Let's see, 2 moles sample of ammonia is introduced into a 1 liter container at a certain temperature. The ammonia partially dissociates according to this equation. So this is effectively the reverse of Haber's process. So that's the balance. No, that's not balanced. Got to balance the equation. And then at equilibrium, 1 mole of ammonia remains. Calculate the value of K. Okay. Let's substitute those in there. Do away with this one. So we got ammonia. And I like to write, like spread it out to make room for the balancing process and the calculations. All right, this is going to be 2 here and 3 here. Okay, the initial concentration, 2 moles sample of ammonia is introduced into 1 liter container. That means it's 2 molar. And there's nothing here or here. That means it's moving to the right. So at equilibrium, 1 mole of ammonia remains. So at equilibrium, we've got 1 mole in that same liter container. So it's 1 molar. That means we know that we lost 1 molar. If we lose 2 molar from here, it has to show up as a half mole here. Right? Because for every 2 of these, you get 1 of those. And for every 1 of these, you get 3 of these. And so this is plus 1.5 molar. All right, so this is 0.5, this is 1.5. So our equilibrium expression, was that the question? Calculate K. Okay. So we got nitrogen, first power, hydrogen to the 3rd power, and ammonia, 2nd power. So nitrogen is 0.5, and hydrogen is 1.5 cubed, and ammonia is 1. Okay. It's getting too late in there. I'm gonna let my calculator do this one. 1.5 and 3. Okay. And then 0.5 times that and divided by 1. Obviously, it'd be 1.69. Let's see if I did that right. Yeah. Okay. Let's see, how we doing on? We're good on time. Should be good on time today. Let's see. We got an dinitrogen tetroxide decomposes into 2 moles of nitrogen dioxide, and the K value is given. 1 mole sample of the N2O4 is placed in a 10-liter vessel and reaches equilibrium. Calculate the equilibrium concentration of N2O4 and NO2. Okay, that should be fairly simple. Didn't need to do that. It's not worked out, is it? I need to do this. Look at the hard copy. No, I didn't make it easy on myself this way. Okay. We can do that. N2O4 gas is in equilibrium with 2 NO2 gas. We have initial chain equilibrium. All right. 1 mole sample in 10-liter vessel. So the concentration is 0.1 molar. And there's nothing here. So we know it's moving to the right. Let's see. So if we lose, let's see, calculate the equilibrium concentration of N2O4. We're going to do both of them, so it really doesn't matter. If this loses 1x, this is going to show up as 2x. Okay? Let's see if there's a simpler way to do that. Now, think about it. This is going to be 2x. Okay? So the equilibrium is, let's see, calculate the equilibrium concentration with K equals 4 times 10 to the minus 4. K equals 4 times 10 to the minus 4, and that's equal to NO2 squared over N2O4. The first power, this is going to be 4 equals 2x squared over 0.10 minus x to the first power. Okay, we might as well go ahead and do all this. So I'm going to take this expression and put it over here. I might as well write the whole thing out so it will be 0.10 minus x equal, this would be 4x squared, right? Now the question is, if this value is very, very small, that means not very much over here is going to be produced. All right, we're not going to lose a lot here. So that means x could be considered very small, much, much smaller than 0.1, right? By 3 orders of magnitude. So if we can say that x is very small, maybe what we can say is we can eliminate that value right there. If it's really, really small compared to 0.1, and say 10 to the minus 1 times that would be 4 times 10 to the minus 5, correct? 4x squared. That means x squared equals 4 divided into that, which would be 1 times 10 to the minus 5, and x would be the square root of 1 times 10 to the minus 5. .16 times 10 to the minus 3. 3.16 times 10 to the minus 3 is x. And then we subtract it from 0.1, and that's essentially 0.1, isn't it? Oh, wait a minute. No, but it's still pretty small. 9.68 times 10 to the minus 2. 9.68 times 10 to the minus 2. And this one would be 2 times x, which would be 6.32 times 10 to the minus 3. 6.32 times 10 to the minus 3. All right. Here's where we can use the 5% rule. We can say, we can plug these values into that and see if it comes close to that. So we're going to say NO2 squared, this one, 32 times 10 to the minus 3 squared divided by 9.68 times 10 to the minus 2 equals what? All right. So this one's gonna be squared, I'm gonna go ahead and split it there. And then divide by this value, so I just split those and divide. So this is 4.13 times 10 to the minus 4. Pretty close. But is it within 5%? So notice they're at the same power, 10 to the minus 4. So really all I need to do is say 0.13 divided by 4 times 100. 0.13 divided by 4. 3.2%, 3.3%. So we're safe. Now let's see what it says. 0.97. Yeah. 0.97, that's right. And then 63210. Okay. Oh, okay. Yeah. I can wait. We haven't got that much left to go. I think this is the last topic, Le Chatelier's principle. How's your dad doing?
Okay, he's better.
He's what?
He's better. Like, I think so. I think I was like he's kind of dying down now he's trying to get out of himself.
Yeah. Is he making progress?
Yeah, he's made a lot of progress.
Yeah.
It's never like disabled physically, like other than his eyesight,
Yeah.
but that's really that only thing that's really put him.
Uh-huh. Yeah. If you can make progress, then it'll lift your spirits. I know my wife's in the middle of recovering from a broken arm. And she made a lot of good progress yesterday during physical therapy. And you can tell she feels a lot better about it. And we figured out how to treat it too. It's been almost 8 weeks since the break. So the bone pain should be gone. The pain she's feeling now is arthritic. It's in the joint that's stiffened up. And we're putting moist heat on it right before she goes to physical therapy, and it's much, much less painful. Yeah. Let me see. Is she taking anything for that? I don't think so. Yeah. Mm-hmm. Celebrex. It's got sulfur in it, doesn't it? She's allergic to any of the sulfur drugs.
Well, I'll be back. I'm like Hollywood,
Mm-hmm.
but I'm not allergic to
Her rheumatologist just threw up his hands. So I don't know what to do with you. You're allergic to all the drugs we have. In fact, he stopped just giving her the drug and having her take it and react to it. He sent her to the blood bank or the whatever and had a hospital. I was sent to the hospital, and they ran an immunology test with her blood and the drug to see if it would react.
do they do that to people with type of face? Like some people with that how they're like how stress react to certain type of faces.
Mm-hmm. Mm-hmm. And she reacts to all of them. So now she has osteoarthritis. Her dad had rheumatoid arthritis. But I'm glad she doesn't have that. Ooh, that's bad stuff.
But it's not bad yet. But I can feel it. Right?
Yeah. And maybe because you caught it early, the treatment would be more effective.
Now they got to try that for me. So I take it to the doctor's like, I'm like, I'm going to take it. I'll just take most of it there. I don't have to take much more. I haven't took any medicine like Tylenol, Motrin, in my 4 years. I don't like medicine. I don't think you do.
That's good.
It's like that. I have a headache. I just rub a little peppermint oil on my head. Yeah, and Tylenol, I can say like, I take it back and get people. It's called all of them.
Yeah. Yeah. Yeah, it's,
I feel that like Tylenol or go back out and work and come out like, if they tell them the APA is gone.
well, they can still, rule against it now, except that they'd be fighting the whole industry. That would be a political problem. Okay, this is the last topic that we're going to cover in equilibrium called Le Chatelier's principle. When we looked at earlier, adding reactant or adding product and looking at the shift, that was Le Chatelier's principle. Le Chatelier said that if a system is at equilibrium and you impose a change on the system that causes the concentrations to shift, it will respond in a way to mitigate that change. So if we go from products to reactants and we add reactant, any reactant, it's going to shift back toward products as a response until you reach equilibrium again. Now there are three types of let's see, I'm searching for the right word. I want to say insults, but that's, you insult the system. But anything that changes concentrations will cause the system to react in such a way as to mitigate that change. The first one is easy. It's concentration. Right? So the system's going to shift away from the added component. If we have A, B, you'll see D, and we add A, it's going to shift towards C and D. And it's going to use up some B to get there. So we shift the position of the equilibrium, but we still don't shift the K. The only way you shift the K is change the temperature. I've got some videos too. Yeah, this one. I was looking for my, here it is.
Le Chatelier's principle states that if you have a reaction equilibrium and you apply a stress to that equilibrium, the reaction will shift in a direction in order to relieve the stress. We will look at a series of different reaction equilibria. We'll apply a stress to those equilibria and see in which direction they shift. In the reaction between iron plus 3 ion and thiocyanate ion, if we add some iron plus 3 in the form of iron 3 nitrate, and to the iron 3 nitrate add some potassium thiocyanate, the two react to form a reddish-orange complex ion. We fill 2 test tubes with the reaction mixture. We're going to keep one test tube as a control so that we can see what happens to the color. To the other tube, we're going to add some 0.1 molar iron nitrate to increase the concentration of the iron. We see that there's an increase in the dark red color. This indicates an increase in the concentration of the complex ion. This also indicates that the reaction has shifted in the forward direction. As you add reactant to an equilibrium, the reaction shifts in the direction to use up the added reactant, in this case the forward direction. Now we'll add 0.1 molar potassium thiocyanate to the second tube. This increases the concentration of the thiocyanate ion. We see that the reaction mixture turns a darker red color, indicating an increase in the formation of the complex ion. We've added the other reactant, the thiocyanate. The reaction shifts in the forward direction to use up the added reactant. We will now add some 1 molar sodium hydroxide solution. We notice that the red color decreases significantly. This indicates that the reaction equilibrium has shifted in the reverse direction. The hydroxide ion precipitates the iron ion, effectively removing it from the solution. The equilibrium shifts in the reverse direction to try and increase the concentration of the iron. We will now add solid potassium chloride to the solution. We notice the decrease in color indicating that the reaction has shifted in the reverse direction. The chloride ion forms a complex ion with the iron, effectively tying up the iron concentration. The equilibrium shifts in the reverse direction to try and replace the iron that's been removed. We will now add 0.1 molar silver nitrate to the reaction mixture. We notice the disappearance of the red color, which indicates that the equilibrium has shifted in the reverse direction. We also see the formation of a small amount of white solid. The silver ion reacts with the thiocyanate ion to form slightly soluble silver thiocyanate, which is the white solid. The silver ion removes thiocyanate from solution. The equilibrium shifts in the reverse direction to try and replace the thiocyanate ion that's been removed. We will now add some 0.1 molar mercury 2 nitrate. The mercury plus 2 ion reacts with the thiocyanate ion to form a new complex ion. This effectively reduces the concentration of thiocyanate in the solution. The equilibrium shifts in the reverse direction to try and replace the removed thiocyanate.
Okay. What this presenter was showing you was the basic reaction is iron plus thiocyanate yields the red colored complex ion. And in order to, you can easily add iron or easily add thiocyanate and shift to the right. But how do you remove the others? So what he's using is called a coupled reaction. He couples another reaction to remove iron or remove thiocyanate and shift it back the other direction. You're going to be doing those next week with this, and this is an informal lab. You don't write a formal report for this one. You just answer the questions in the hard copy. But when you do, and you answer the questions, be sure to write your equation that you're referencing when it says which way does it move. What's your explanation for the observed change? If you're going to say move to the left and move to the right, you need to reference an equation. So write the equation in there in your answers so you can say it moves one way or the other. Okay. All right. Well, you do have one due. Right. No, not a formal report. No, just study the hard copy and be ready to, because there are a series of different qualitative reactions that you're going to do. It's not quantitative. All right, that was a change in concentration. So what happens when you change the temperature? Actually, when you change the temperature, you change the K. And when you change the K, that in itself will shift the equilibrium. There are two ways to approach this, and I've got a video that's going to approach it from the true change in K direction. But as a practical matter, Oh, it's raining.
I'm saying that I have this.
You got more than one copy. If you have a reaction that, well, let's use the Haber process. Right, N2 plus H2 yields NA3, and this is 2, this is 3. So this reaction is exothermic. That means that as you go from reactants to products, you give up heat. And the way I like to approach it is to put the heat in as a term, either a reactant or a product. If it's exothermic, then the heat ends up over here, right? It's stored over here somewhere. And when you react, you give it up. If you do that, then regardless of what the K is, if you change the temperature, you're changing the amount of heat. So if I say increase the temperature, then I'm increasing this factor, and that drives the reaction back that direction. For endothermic reactions, we put this on the other side, and if you increase the temperature for those, it drives it to the products. So that was Haber's problem. He increased the temperature. Remember, we had the 10 to the 4th K for this reaction at a low temperature. He increased the temperature, it completely shifted it that direction. He changed the K. So I don't know if I've mentioned how he got around that. The reason he increased the temperature was so that there would be enough energy for the reaction to proceed. But at the same time, he shifted the equilibrium, right? So he had two problems. He had a kinetic problem and he had an equilibrium problem. He solved the kinetic problem by increasing the temperature, right? And they would exceed the activation energy. But it would also shift the equilibrium back the wrong direction. So the way he got around it was, he's at, I think it was 800 degrees C. What he did was he added a catalyst, finely divided iron, and that made the reaction proceed faster to the right. But it wasn't enough in and of itself to produce enough efficiency. So what he did was, these are all gases, gases. He knew the boiling point of these gases. The boiling point for these guys right here is very, very low. You got to get really cold to condense them. But you don't have to get as cold to condense ammonia. So he had a bleed line coming off of his reactor. These are all gases. So he just gradually bled off reactants and products and ran them through a cooler just cold enough to condense this one. This one dropped out of solution as a liquid, or dropped out of the mixture as a liquid. And then he funneled these two back into the reactor. And he just kept cycling it like that. And increased his efficiency into an economic range. Okay. So this is going to be our explanation.
This is MSJ Chem. In this video, I'll be looking at Le Chatelier's principle and temperature. Changes in temperature cause a change in the equilibrium position and in the value of the equilibrium constant Kc. Here we have the chemical equation for the Haber process. In the Haber process, nitrogen and hydrogen react together to form ammonia. The forward reaction of the Haber process is exothermic. This can be seen by the negative value for the change in enthalpy. If the forward reaction is exothermic, the reverse reaction is endothermic. We can see this by looking at the sign of the enthalpy change, which is positive. So when we use Le Chatelier's principle to predict in which direction the equilibrium position will shift, we need to know if the forward reaction is endothermic or exothermic. If the forward reaction is exothermic, the reverse reaction is endothermic, and vice versa. Next, we'll predict in which direction the equilibrium position will shift when the temperature is increased. When the temperature is increased, the equilibrium position will shift to the left, which is the reactant side. And the reason for this is that the system will absorb the extra heat, favoring the reverse reaction, because it is endothermic. When the temperature is increased, the reverse reaction will be favored because it absorbs heat. Therefore, the equilibrium position will shift to the left, in the endothermic direction. Next, we'll predict in which direction the equilibrium position will shift when the temperature is decreased. So when the temperature is decreased, the equilibrium position will shift to the right, which is the product side. And the reason for this is that the system will produce heat favoring the forward reaction, because it is exothermic. When the temperature is decreased, the equilibrium position will shift in the exothermic direction, which is to the right. Next, we look at the effect of temperature on the value of the equilibrium constant Kc. So for an exothermic reaction, increasing the temperature shifts the equilibrium position to the left and decreases the value of the Kc. So as we saw in a previous slide, the forward reaction of the Haber process is exothermic. Here we have the equilibrium constant expression for the Haber process. When the equilibrium position shifts to the left, the value of the numerator decreases and the value of the denominator increases. Therefore, the value of the Kc decreases. So an increase in temperature for an exothermic reaction results in a decrease in the value of the Kc. For an endothermic reaction, increasing the temperature shifts the equilibrium position to the right and increases the value of the Kc. Here we have the reaction between hydrogen and carbon dioxide to produce water vapor and carbon monoxide. As we can see from the sign of the enthalpy change, the forward reaction is endothermic. And here we have the equilibrium constant expression for the reaction. When the equilibrium position shifts to the right, the value of the numerator increases and the value of the denominator decreases. Therefore, the value of the Kc increases. So for an endothermic reaction, an increase in temperature results in an increase in the value of the Kc. So let's end with a summary, starting first with exothermic reactions. When the temperature is increased, the equilibrium position shifts to the left and the value of the Kc decreases. And when the temperature is decreased, the equilibrium position shifts to the right and the value of the Kc increases. And finally, for endothermic reactions. When the temperature is increased, the equilibrium position shifts to the right and the value of the Kc increases. And when the temperature is decreased, the equilibrium position shifts to the left and the value of the Kc decreases.
Okay. So the quick way to figure out which way it moves is actually based upon the change in K. All right. The third way that we can stress the system is through a change in pressure. Now, change in pressure will only affect a system that has gases involved. The change in pressure on a solid or a liquid system, or even on an aqueous solution, and none of the reactants or products are gases, then the change in pressure will have no effect on them. And even if they are, let's try to take an example. Let's say, I hope I got an example. No, I don't. If you increase the pressure by injecting an inert gas, that will have no effect on the equilibrium, because the inert gas is not a reactant or a product. But if you increase the pressure by injecting either reactant or product, it depends on the mole ratio of the reactants and products. The other way, actually, the best way to investigate pressure change is by changing volume, because that way you don't inject any reactants or products into the mixture, and then you're working from the concentration change angle then. But if you just change the pressure of a pre-existing mixture by changing the volume, then you look at the mole ratio of the reactants and products. Yeah, let's use this one. The Haber process. Okay. We're going to change the pressure by changing the volume. So if we squeeze the mixture, it's at equilibrium, and we squeeze the mixture, what's going to happen? Well, you have 2 total moles here. Then you have 4 total moles of gas on this side. So if you reduce the volume and increase the pressure, what you're going to do is force the system to react in a way that will drive it toward the smaller number of moles. And that will, you add pressure by decreasing the volume. So if it makes fewer moles, then that's going to relieve some of the pressure. In fact, that's part of what Haber did also. I left that part out. He increased the pressure by several, I don't remember exactly how many, but a number of atmospheres pressure. Okay. So let's see what this one has. It's the same guy talking. Oops, what happened? There it is.
The pressure of a system can be changed by either adding or removing a reactant or product, or changing the volume of the reaction vessel. The first point has the effect of increasing the concentration of the reactants or products. The second point refers to Boyle's law. Boyle's law states that pressure and volume are inversely proportional at constant temperature. This can be written in equation form as P times V equals constant K. Changes in volume will affect the pressure of the reaction vessel. For example, if the volume of the reaction vessel is increased, the pressure will decrease. And if the volume of the reaction vessel is decreased, pressure will increase. It should be noted that changes in pressure only have an effect on the equilibrium position when there are different amounts of gaseous molecules in the reactants and products. So next we look at some examples. The reaction we'll look at is the Haber process, in which nitrogen and hydrogen react together to form ammonia. In this equation we have 4 moles of gas on the reactant side and 2 moles of gas on the product side. This means on the reactant side we have more gaseous molecules, and on the product side we have fewer gaseous molecules. When the position of equilibrium shifts to the side with a fewer number of gaseous molecules, this results in a decrease in pressure. And when the position of equilibrium shifts towards the side with a greater number of gaseous molecules, this results in an increase in pressure. So when we make predictions about in which direction the position of equilibrium will shift for changes in pressure, we need to consider the number of gaseous molecules in the reactants and products. So in the next example, we'll predict in which direction the equilibrium position will shift when the pressure is increased. An increase in pressure shifts the equilibrium position to the right, which is the product side. So the equilibrium position will shift to the right because there are fewer gaseous molecules on the product side, which lowers the pressure. As we saw earlier, there are fewer gaseous molecules on the product side of the equation. When the pressure is increased, the equilibrium position shifts to the side with a fewer gaseous molecules, which has the effect of lowering the pressure of the system. Just like for changes in concentration, changes in pressure do not affect the value of the equilibrium constant Kc. In our next example, we'll predict in which direction the equilibrium position will shift when the pressure is decreased. When the pressure is decreased, the equilibrium position shifts to the left, which is the reactant side. So the equilibrium position will shift to the left because there are more gaseous molecules on the reactant side, which increases the pressure. Because we have more gaseous molecules on the reactant side, an increase in pressure will shift the equilibrium to the left. And once again, the value of the Kc does not change. In our last example, we look at changes in pressure when there are the same number of gaseous molecules in the reactants and products. So in this reaction, we have 2 moles of gas on the reactant side and 2 moles of gas on the product side. So the position of equilibrium will not change because there are the same number of gaseous molecules on both sides of the equation. So if we have equal numbers of gaseous molecules in the reactants and products, changes in pressure have no effect on the position of equilibrium. So let's end with a summary. In this table, we have change to the system at equilibrium, change in equilibrium position, and change in the value of the Kc. When the pressure is increased, the equilibrium position shifts to the side with fewer gaseous molecules. When the pressure is decreased, the equilibrium position shifts to the side with more gaseous molecules. And changes in pressure when there's equal numbers of gaseous molecules in the reactants and products has no effect on the equilibrium position. And as we can see, the value of the Kc does not change when changes are made to the pressure of the system.
Okay, I think that's it. Yep. Stop share. Comments or questions? That wasn't too bad, was it? No, equilibrium. After kinetics, equilibrium is a cakewalk.